So last time we looked at a spherical conductor, a spherical distribution of charge on the charge. So if you have a spherical conductor and there's some charge on it, all the charge goes to the surface. And we also mentioned that there will be some solid space sphere of charge. So I'll first look at this and then non-uniform charge solid sphere, and then get the question sent to me. So I'll start with example 22-4. This is solid sphere of charge. So we have some solid sphere. Okay. Something better. And there's some charge on the sphere, and it's distributed uniformly. It's not just a spherical shell, it's a full sphere. So this has to be an insulator. If it was a conductor, then all the charge will actually move to its surface. If it's uniformly charged, it means that there's charge everywhere in every piece of this sphere. So it must be an insulator. This is sometimes given, sometimes not. Sometimes you have to deduce it, and sometimes it's explicitly told. Now, we have an electric charge Q distributed uniform to a non-conducting sphere of radius R naught. So its radius is given. In this figure, a determined electric field outside the sphere and inside the sphere. So two cases, and inside the sphere. Now, outside the sphere, we kind of already solved. Okay? So I already told you that for a spherical charge distribution, something similar to Newton's theorem for gravity is applicable. And what is going to happen is that this is going to act like a point charge at its center. But let's do this again, just formally. We're going through steps, and we're going to, of course, apply Gauss's law. And to apply Gauss's law, I'm going to choose a Gaussian surface. And the Gaussian surface, appropriate for this problem, is a sphere concentric with our charge distribution. Okay? Now, why is this? Because we want to apply this formula, Gauss's law. dA is Q enclosed divided by epsilon naught. But we don't want to take this integral. If we have to take this integral, it's going to be quite hard. So we don't want to take the integral. What we want to do is we want to simplify things. And to simplify things, we first need to get rid of the dot product, and then take this electric field outside the integral. Now, then to do that, sometimes we will need to divide the integral into parts, but we have to choose some surface where this normal element, the normal vector to the surface is going to be either parallel or perpendicular to our electric field. If we do that, then the dot product becomes very simple. When they're parallel, it's just a normal product. When they're perpendicular, it's just zero. Okay? Or it should be a known angle, right? That case is rare, but we somehow have to get rid of this dot product. If we have to, take this surface integral honestly, then you should not use Gauss's law. You are much better off using Coulomb's law. But we want to use Gauss's law, so we want to choose a Gaussian surface where this is simple. And this is exactly a situation like that. So the normal vector to the little surface elements that we choose on this Gaussian surface is going to be perpendicular to it, and hence in the radial direction. Okay? And by symmetry of the charge distribution, we also know that the electric field should be in the radial direction. It cannot be in any other direction, right? So the electric field over here has to be perpendicular to this spheres concentric with the charge distribution, because when I rotate those spheres, when I rotate the charge distribution, nothing should change. If it was not in the radial direction, but there was also some tangential component, some transverse component, and as I rotate it, then the electric field will change. The only way for electric field not to change is if the electric field is in radial direction everywhere. Right? So choosing a surface like this is going to simplify this dot product. That's the strategy. And I know I'm laboring too much on this, but it's the same thing that you do again and again for different, more complicated problems. Now, as we do that, let's assign a radius to our sphere, our spherical surface as well. And the electric field and the normal to the surface. So this is the normal. And this is, of course, parallel to our dA, right? So the dA is just dA times the normal vector. So these are parallel, so this just becomes a simple integral. Okay, this is a simple product the dot finishes, and because of the symmetry of the charge distribution, the electric field not only should be in radial direction, but it should have the same magnitude everywhere on the sphere. Right? And this electric field is evaluated at the surface point. This is how Gauss's law works. And the electric field magnitude should be the same because it's equidistant from the charge distribution. Right? So everywhere, it sees the same charge distribution. Over here, I see a sphere some distance. Over here, I see the same sphere of some distance. So the magnitude of the electric field is going to be the same, which means I can take this out of the integral. EA, and now the integral is trivial. It's just the surface area of the sphere. Okay, this way, E times 4 pi R0 squared. And this is equal to the charge enclosed. Well, the charge enclosed in this case is the whole charge. It's just Q divided by epsilon naught. And as I said, this is going to be Q over 4 pi epsilon naught R0 squared. Now you can stop here, and the book actually stops here. Yeah, it does stop here, but you can go a little bit further. They're asking for the electric field, and electric field is a vector quantity. This is just the magnitude, but it doesn't actually tell you what it is. So you can say something like, so the electric field is going to be in the radial direction. So this R hat is the unit vector in the radial direction, or wait, sorry, this is R squared. So that R hat is the unit vector in the radial direction. So you can write it this way, or equivalently, you can write it this way. You're going to see both of these probably. Okay, so R hat is a unit vector. Its value is given by this. So either of these is acceptable. They both have their uses. Sometimes one is more convenient to use, sometimes the other. But electric field is a vector quantity, so it's better to give your answer in this form. Any questions? Anything about the strategy that you're uncomfortable with, that you want me to go over again? This is very simple. So if there's a problem here, we can immediately identify it. And it will be easier to attack when there are no other confusing issues.
Hocam, I couldn't understand last part, which is R equal.
This one?
Yes.
So this is definition. So R hat, typically, and this is the convention that's used in the book, this is the convention used pretty much everywhere in physics. A little arrow on a quantity indicates it's a vector. A little hat on a quantity indicates it's a unit vector, meaning it is a vector. It is something with a magnitude and a direction, but its magnitude is always 1. That's what a unit vector is. So this R hat will be the unit vector in direction of R. So I take R, I divide it by its magnitude. So the resulting vector, by definition, has to be of unit magnitude, of magnitude 1. And I call that R hat. So this indicates the direction. It doesn't change. So this vector, this whole vector, has this magnitude, Q divided by 4 pi epsilon naught R squared, which is the magnitude of the electric field. And the direction of the electric field is in radial direction outwards. This is what that indicates. So you can take this and combine them. You can say that R hat is just the R vector divided by its magnitude, and write it this way. So this R squared becomes R cubed, and this R hat becomes R vector.
Okay,
it's something
thank you.
we will see again and again. Sure.
I understand we define vectorial.
Yeah. So the book just leaves this magnitude, but I think it's better to move to the vector. Now let's confuse the issue a little bit, or make the issue a little more complicated, and look at the inner part. Okay? So let me switch to another. So I'm going to draw another Gaussian surface. Again, of radius R, but this time R is less than R0. And the same thing happens here. This is a closed sphere, so I'm going to have these little dAs over here. They'll all have this normal vector. And so this normal vector is changing direction as I move on the sphere. And these relations are going to hold. Now, again, because of the a spherical distribution of the charge, the electric field on the sphere should also be in the radial direction. Now here, intuitively, it's obvious that it has to be radially outward because the electric field originated positive charges and terminated negative charges. If everything was going in, well, they have no place to terminate. There are no negative charges inside. Right? So it has to be outward. Here, it's not obvious, right, which direction this is going to be. But again, you'll see that it is going to be outwards. And now we proceed in exactly the same way. So because the electric field is in the radial direction and my surface area dA is in the radial direction, the dot product becomes a simple product. Right? And again, because everywhere I move on the sphere, I see the same charge distribution, the magnitude of the electric field should be constant as I move on the sphere. So I can take this E out. And this becomes a simple integral. And this is just going to be E4 pi r squared. Now the right-hand side changes. Now, previously I was outside, so my Gaussian surface enclosed all of the charge. Now I'm inside. The enclosed charge depends on the radius of the sphere. It's not the whole charge. Okay? Now, what is it? Well, it is something proportional to the whole charge. It's going to be the whole charge times the radius of the sphere I have chosen, cubed, divided by the radius of the whole charge, cubed, divided by epsilon naught. Now, how did I get this one? How did I get this ratio? Well, the Q inside over Q total has to be V inside divided by V total. Okay. Why? Because if I multiply all of these by my charge density, then this works, right? So Q inside is nothing but the volume inside times the charge density, and total charge is nothing but the total volume times the charge density. Okay? So both of the regions for both the total volume and for the sphere that I'm considering, spherical surface I'm considering, I have a single uniform charge density. So what I do is that I cancel these out. And I say that the ratio of the charges is just the ratio of the volumes. But the volume is proportional to R cubed. In fact, it's just 4 pi, let me erase this. 4/3 pi, sorry. 4/3 pi R cubed divided by 4/3 pi R0 cubed. And the 4/3 of course cancel. And I end up with this, the ratio of the charges is just the ratio of the cubes of the radii. And that Q total is nothing but Q, I move this to the other side, Q inside enclosed charge is capital Q times R cubed divided by R naught cubed. Okay. Now I get a slightly different expression. Right. So I'm going to have some cancellation. This R squared is going to cancel part of this R. I'm going to end up with, I think, Q times R divided by R0 cubed. Right, so the 4 pi epsilon naught is there, R squared cancels R real. And again, I want to attach a direction to this. Okay, the electric field is going to be, so what does this tell you? First of all, if you look over here, so this, maybe it's better if we take back one step. So erase this and rewrite it in a form that I can interpret more easily. So the
May I ask a question?
Yeah, go ahead.
Was our sphere hollow or solid?
It's solid. It says so in the example. The example is solid sphere of charge.
Okay, thank you.
So this was the electric field was Q enclosed divided by 4 pi epsilon naught R squared. You know, what does this tell you? When I have a spherical charge distribution, okay, at a given point within that charge distribution, I only see the effect of the charge that's inside. The outer spherical shells do not contribute. Okay? So this is again same as the Newton's theorem in gravity. right? If you have spherical mass distribution, to the outside, it's going to act like a point mass at the center. To inside, it acts like nothing. There is no force applied. Same deal here. The outer shells do not contribute. There's no contribution. As long as they're spherical symmetric, their effect just cancels out. When the charge inside, however, contributes like a point charge at its center. Okay? And then we take this Q enclosed and attach this value, and we get this expression. Okay? Now, again, I want to attach a direction to this. How do I do that? Well, again, if I think about this, the effect on the surface of the sphere is originating purely from these charges that are inside, and the electric field produced by those charges is going to be similar to the electric field produced by the full solid sphere. It's radial outwards. So this is also going to be in the radial direction, which means that E and R are going to be in the same direction. So it's automatically takes care of the situation. If Q is negative, then this is just reversed. Okay? Just like the case before. Are there questions now? So this is a bit more confusing for two reasons. First, the charge distribution, the charges needs to be calculated. And second, you have to make an argument for the direction. Does either of these cause any difficulty? Okay. The next example here is a non-uniformly charged solid sphere. So far we have been assuming that this is just uniform. It's a constant. Now, to be able to apply these techniques, this is kind of an overkill. This is too much. You don't need this much uniformity. What you need is just spherical symmetry. But in principle, your distribution, your density could depend on the radius. So at different spherical shells, you could have different charge densities. As long as it's spherically symmetric, most of these arguments are going to apply. Now, what's going to be complicated is the calculation of the charge. Okay? Remember, for the calculation of the charge, I've written this, Q inside by Q total is equal to the V inside by V total, because both of these hypothetical volumes have the same uniform charge density within them. Now, if the charge density is not uniform, then you can't make the simplification. You have to actually honestly calculate what the charge enclosed is. And so let's move on to that, if there are no questions here, and try to tackle that problem. Shall I move on to that problem? Okay. Now, if this is so complicated that there's also no spherical symmetry, then you're kind of in trouble. Either you need to be able to divide the problem into sub-problems which have certain symmetries. Like it could be that you have a sphere, but the cylinder is just hollowed out. That you can do, because you can calculate the electric field of these two separately, and then use superposition to add them, which I'm going to show today, actually. But if there is no such thing, if there's just some arbitrary looking charge distribution, then you don't use Gauss's law. Gauss's law is applicable when you don't need to take that integral. Okay? Or it's useful when you don't take the integral. It's always correct. It's always correct. But when the integral is so complicated, you might as well just write an integral for Coulomb's law. Okay, so this is example 22.5. Which here, non-uniformly charged solid sphere. Suppose the charge density of the solid sphere in this figure that I already drawn and traced is given by rho of E alpha r squared. R squared. So I have a sphere. Of radius r naught again. And of charge Q again. But now the charge is not uniformly distributed, but it's distributed in some sense proportional to r squared. The density of the charge is proportional to r squared. So at the very center, the charge density is 0. At the surface, it's alpha times R0 squared. Now, the first question is find alpha in terms of the total charge Q on the sphere, and its radius R0. So what's alpha? Okay, so alpha in terms of Q and R0, and find the electric field as a function of R inside the sphere. So E is a function of R, is this where R is less than R0, right? This time they're not asking the case R larger than R0 because that will proceed exactly the same as the solid charge. It doesn't matter that there's some radial dependence, as long as it's spherical symmetric, a charge distribution to outside is going to look like a point charge at the center. So this time they're not bothering asking this. So let's start with this one as alpha as function of Q. Now, how would you proceed this? So you're given a density function that includes alpha, and you're given the total charge. How would you proceed? What would you do?
Total charge is equal rho times V. I mean, volume.
Let's go with this. So total charge, let's call this Q, is rho times V. Is this correct? Does anyone have any objection to this? Now, what is rho? This is alpha times R squared. What is V? That's 4/3 pi R0 cube. And so I can write alpha in terms of these quantities. So alpha is going to be Q divided by R squared, 4/3 pi R0 cube. Is this the answer? Does anyone have an objection to this? Now, I told you that they're asking us to find alpha as a function of Q and R0. Here it's Q, R0, and R. 4/3 and pi are constants, so it doesn't depend on them, but it depends on R. So what does this mean? At different R's, we have different values for alpha. But alpha is a constant, they told us. It doesn't depend on R. It depends on the other constants, the total charge and the radius of the sphere.
So if we are trying to calculate the density from the center to a radius, an arbitrary radius, let's call it R, then we need to take the sum of all the densities in dr. What I'm trying to say is we need to use integral from 0 to R.
So you're saying that rho is in fact rho of R integrated from 0 to R0. Is that what you're saying? Rho total. Is this what did I understand correctly?
Yes, this is what I meant.
Okay. Will this work? We can certainly take the integral. Alpha R squared integrated from 0 to R0 is going to be alpha R0 cubed divided by 3. Okay. And I can substitute that over here instead of this. Alpha R0 cubed divided by 3. And I can put this in, and indeed the R dependency goes away. Is that how it's going to be?
Hocam son dediğinizi anlamadım. Tekrar edebilir misiniz?
So the result of this integral, if I take this with this value, it's going to be alpha R0 cubed by 3. Yes. So I take this and substitute this in here. Instead of alpha R squared, I use this value that I just calculated. And then I solve for it. And there is no longer R. Okay. So instead of this, I will have R0 cubed by 3. So it's no longer depends on R. Is this correct though? Is this how you would approach this?
I actually thought of something different.
Okay, what did you think of?
Since actually the density is the one that is changing, right? And we don't, and is Q constant, by the way? I don't think Q is
Q is constant, yes. Q is a constant. So it's a total charge.
I was actually trying to, oh, then if we take the integral of Q, like integral Q is equal to integral of rho times V, right?
Almost, but you're on the right track. So Q is not rho times V. This is, when is this correct? First of all, let's see where this is correct and where it fails and how it fails. When is total charge is the density times the volume?
When it's
the R
uniform.
is,
When it's uniform. When it's not uniform,
But here
what
is
do you
not
do?
uniform, so you should use integral.
Yes.
That's
So-
why we
Go
can
ahead.
write instead of rho alpha times R square with integral.
So you want something like this. I'm going to integrate alpha times R square over what? So what's the little things?
dv hocam. For example,
The
we
little
can
volume.
choose a shell sphere inside the solid with thickness dr, and the boundaries of integral will be 0 from 0 to r 0. I mean,
Yes. Okay. Now, what is this? So this is a very general strategy that we already deployed, and we're going to deploy again and again and again and again. And as engineers, you're also going to deploy this. So you have some formula that is valid for the uniform case. Okay? The charge in a given region is the density of charge times the volume of that region. If the density is uniform. If it's not uniform, what do? You take this region, you chop it into little pieces, such that they become so small that in those little regions, in those infinitesimal regions, the density is uniform. Why is it uniform? Because it's very small. It doesn't have a place to change, right? Let's say it changes from 5 coulombs per cubic meter to 3 coulombs per cubic meter over 1 meter. Over half a meter, the change is going to be half of this. Over a centimeter, it's going to be 100 of this, and so on and so forth. Okay? So if this is infinitesimal, the charge density cannot change. The charge density is going to be uniform, which means that my formula is going to hold, but it's going to hold in an infinitesimal form. The infinitesimal charge in that infinitesimal region is going to be whatever the charge density in that infinitesimal volume is times that infinitesimal volume. And the charge I get is going to be obtained by integrating this. Q is going to be integral of this dq, and I'm going to need to integrate this over my whole system. Now, one thing is that, so this is presumably given, or you calculate this some other way, but what is this? How do you calculate this one? Now, our formula here is given as function of r. So I want to look at situations, as long as I keep the same constant r, then I'm going to have a well-defined value for this density. If I let my dv have different radii, then I'm dead. Okay, I can't use a single formula in front of this. My dv has to have a constant r. Now, one possibility that you can do is that you can choose little cubes. Okay, you can try to take little cubes and integrate this all over, but this is not going to be very efficient. You're going to need to take 3 integrals, right? One in the radial direction, one in the azimuthal direction, and one in the polar direction, 2 angles and 1 length. What you can do instead is to take spherical shells. Okay? So something like this. And these are going to have some thickness dr, infinitesimal shells, and they're going to have radius r. Okay? And I'm going to let this r change from 0 to r0, and by this way, I'm going to cover the whole solid sphere. This is the strategy. Now, how would you write the volume for such a spherical shell? Now, we did this for a circular strip. Now, we need to do this for a spherical shell. And for that, again, so remember, for the circular strip, we just open this up and said that this becomes like a rectangle of thickness dr. And the length of the rectangle is going to be the circumference of the circle that we started with. Okay? Something similar here. I take my spherical shell, I open this up, and it's going to become like a slab. And there's going to be a surface area of the slab, which is going to be just the surface area of the spherical shell. And there's going to be a thickness of the slab, which is just dr. Okay? And the volume of that slab is then going to be just the thickness, which is 4 pi r squared, the surface area of the spherical shell, times the thickness. Okay. So this is the area of slab, and this is the thickness of the slab. Okay. So that's going to be my dV. This is how I'm going to proceed. Are you with me? Did I lose anyone? I must have. This is not trivial. This is quite confusing. It's the first time you're seeing it. So if I lost you, where did I lose you? Okay. Right. So I take this and put this in. Okay. And the way I cover the sphere by using these little dVs is if my r, the radius of those little spherical shells, go from 0 to the radius of the solid sphere. So IQ then becomes an integral of from 0 to r0. Let's write it in the order over here. Alpha r squared times 4 pi r squared dr. And that integral can be done. Since alpha and 4 pi are constants, they get out. So alpha and 4 pi. The integral of r to the fourth is r to the fifth divided by 5. So this is going to be r0 to the fifth divided by 5. Do we agree? Did I take the integral correctly? I hope so. And that's equal to q. And now I can write alpha in terms of q. So therefore, alpha is going to be 5q divided by 4 pi r0 to the 5. But at least it agrees with the answer given in the book, so I'm confident that we don't make a very big mistake. All right, so how does it sound? Does this make sense? Is there a confusing part that I can try to clarify? This is not trivial. There are a lot of, thinking, there are a lot of steps that you need to put together. And the trick to be able to put these together is that solving a lot of similar problems. Right? If you have to think about every step, then there's no way you can get to the end. And we are going to make this more complicated. So there are a couple of ways to make this more complicated. One is to consider a sphere as hollowed out. Not a full one, but a spherical part that's just taken out. Another one is to make this function a bit more complicated, right? Or make you calculate that function in some way, so on and so forth. And finally, this is probably not going to be what they're asking. They're going to ask, the question where you need to calculate this, and then you need to use it to get the final answer. Right? And as I said, if you have to think about every step, then you're not going to manage. Some of this has to become automatic, and that requires doing lots of exercises. One thing is, if you think this calculation is too complicated, and the actual question requires you to make that calculation, you will think that you're thinking wrong, because it's so complicated that they will never ask this. But if you think of this as easy, something doable, maybe tedious but still straightforward, then you would actually be on the right track. This is very important. You have to use your intuition when you're solving a problem. You obviously don't want to spend half an hour on part of a problem and realize that that's the wrong way to go. And that intuition is led by how difficult the path you're taking is. Okay? In an exam, they're not going to ask you a problem that's going to take 5 hours to solve. So if you think this takes 5 hours to solve, you'll never get into that path. You have to realize it takes 5 minutes to solve. Okay? And that requires exercise. That's not obvious.
I have a
Okay.
question.
Go ahead.
I understood the steps, but I don't understand why thickness is dr. Is it really related to radius?
Yes. So this is first of all, I have to make the thickness infinitesimal. So I'm going to make a constant radius. Okay, if my thickness is finite, then 2 sides of this shell is going to have different densities that I don't want. So it has to be infinitesimal. Now, what could I say? I could say this is just dl, but then I'm integrating over some variable, right? And it's best to think of this in spherical polar coordinates or spherical coordinates, where there's a radial coordinate r, and there's a azimuthal coordinate phi, and there's a polar coordinate angle theta. And so when you think of this, any movement in the radial direction, an infinitesimal movement in the radial direction, is going to be dr. Okay? And your variable going from the center to some finite distance from the center is going to be r. It's you're moving in the radial direction. So it's not obvious that it has to be this way, but the thickness corresponds to a motion in the radial direction, an infinitesimal motion or infinitesimal displacement in the radial direction. So we call it dr. Okay? And we also call this variable r because, well, that's what spherical coordinates are called. I could call these something completely different, but it's best to think in terms of things that you already know. I'm presuming you know spherical coordinates. If you don't, then well, learn them. You have to learn them. Did you see spherical coordinates in calculus course or some other course?
I don't remember, but maybe we see it.
Okay. So from x, y, z to r, theta, and phi. So this is the Cartesian coordinates. This is the spherical coordinates. You have to learn this at some point. I can't take time to explain it in my course, but this must have been covered in calculus, and probably if you are taking some math course for engineering, must be covered there. Okay, so the second part, calculating the electric field. Now this we proceed in a similar fashion. Okay? So I'm going to draw a Gaussian surface. I'm going to call this radius r as well, hoping this is not going to cause any confusion. And I'm going to just say that, no, from my previous result, this is a spherical charge distribution. The electric field is going to be produced only by the charge inside. The charge outside, because it's spherical symmetric, does not contribute to the electric field. And the charge inside acts like a point charge. That's 10. And so let's erase this. And I'm going to erase this as well. I'm going to keep this though, because I'm going to use it. Yeah. So the end result, after you go through, drawing the Gaussian surface, this, is going to be the electric field is Q inside divided by 4 pi epsilon naught r squared. And the $1,000,000 question is what's Q inside? Well, the Q inside can be calculated by the same method that we did. I take this part of the sphere that's inside my Gaussian surface, divide it into spherical shells, and integrate out. Okay? So the Q inside is going to be, this time integrals from 0 to r. So perhaps not to confuse you, let's make this capital R. And it's going to be my rho of r times 4 pi r squared dr. Yeah. It is somewhat a confusing practice to keep the limits of the integral same as the variable inside the integral. It is done, but let's try to avoid this. That's why I changed the variable. Okay, now I know this already. So this is from 0 to some capital R. This rho of R is 5q divided by 4 pi rho 0 to the 5th. This is my alpha times R squared times 4 pi times R squared times dr. And I have some cancellation. Now I can erase this. I substitute this in. But yeah, let's make the cancellation first. So I'm going to have these constants out. 5q divided by R0 to the 5th. I again have the same situation. It's R to the 4th being integrated. So this is going to be capital R to the 5th divided by 5. And the 5s are also will cancel. Okay. So previously, when we had uniform charge, this was just the total charge and the ratio, the cube of the ratios. Now our charge density goes as R squared, and it's not the cube of the ratios, but the 5th power of the ratios of the radii. Okay. And then we just put this in there. So this is Q R to the 5th divided by R0 to the 5th divided by 4 pi epsilon naught R squared, and this becomes Q times R cubed by 4 pi epsilon naught R0 to the 5th. Okay. And again, this is compatible with what's given in the book, so I have some confidence there. Now, again, I would like to okay, before I attach a direction to this, you might as well, go back to what is given in the book and turn this capital R into small r. Okay, this is just fixing notation. Temporarily, I make my small r capital R, so this integral will not be confusing. But then, if something is given in the problem, then you have to use those quantities. So I'm using a small r. Now I want to attach a direction to this. Okay. The electric field, again, from the argument for the solid sphere, is going to be in the radial direction. So let me erase this completely. The vector electric field here is going to be Q R cubed by 4 pi epsilon naught R0 to the 5th R hat. This is Q. Or I can absorb one of these into that, and I'm going to have Q R squared by 4 pi epsilon naught R0 to the 5th times R. These are the same thing, just the definition of R hat. And that's how I will give the electric field inside this sphere.